All right. So today's support class is to start getting us ready for Chapter 10 in the parent class. Chapter 10 is by far the biggest chapter we cover in that class, and we spend the most time there. In fact, you can kind of think of chapters 7 through 9 as sort of build up to preparing us pretty much all for Chapter 10. Chapter 10 is dealing with applications of all of the trigonometry we have dealt with, and we look at a lot of different applications. The first two sections in Chapter 10 deal with something called oblique triangles. An oblique triangle is a triangle that is not necessarily a right triangle. It can be any right triangle. In fact, some books will define it as a triangle that is not a right triangle. The reason we're singling out oblique triangles is because up until this point, the majority of the time that we have needed to use a triangle for something, it has been a right triangle. And the reason for that is because our trigonometric functions back in Chapter 7 were originally defined in terms of right triangles. We understand them in terms of the legs and the hypotenuse, different ratios of those values in a right triangle. But now we want to do some work that's similar to what we did in Chapter 7, solving for missing sides or angles of a triangle, assuming that triangle is not necessarily a right triangle. So this is going to sort of introduce us to some of those concepts before we jump into the work that we do in Chapter 10. And we're going to talk first about a couple of different facts regarding any triangle. So the first fact, I think this is sometimes called the Hinge Theorem. It says this: the sum of any two sides of a triangle is always larger than the third side. Now, we could do a geometric proof for this fact, but it's actually very easy to see why this is true. Sorry, I called this the Hinge Theorem. I'm mistaking that with something else. This is normally called the Triangle Inequality because I can write it in the form of an inequality. But the theorem here is actually very easy to see why it's the case. If I look at any two sides of this triangle up here, say side A and side C, and then if I look at the third side, side B, these two sides together can be thought of as a path taking me from this vertex of my triangle to this vertex. Side B can also be thought of as a path taking me from this vertex to this vertex, or this point to this point. Now, we know that the shortest distance between any 2 points is always a straight line. If I take this detour here, then I know that this path from along C and then along A to get from alpha to gamma here has to be a longer path than the straight line. And that's basically what this fact is saying. This third side has to be shorter than the sum of the other two sides. So we're going to use that fact in a moment, but one thing I want to mention here is a labeling convention that we use for oblique triangles. All throughout Chapter 10, but primarily in the first two sections, when we deal with triangles, the sides are always going to be labeled A, B, and C, and the angles are generally going to be labeled alpha, beta, and gamma. Sometimes we'll see those replaced with a capital A, B, and C as well, where the sides are lowercase. In addition to that, there's a convention that's always followed. Side alpha, or angle alpha, and side A are always opposite each other. So you notice side A is opposite angle alpha, side B is opposite angle beta, and side C is opposite angle gamma. And that's because alpha, beta, and gamma are basically the letters A, B, and C in the Greek alphabet. So they correspond to the A, B, and C in that way. You have to remember that convention as we work through all of these problems, because I'm going to be asking a lot of questions referencing this triangle without redrawing it every time. One final thing to mention here, this H right here. H stands for height, but we can also say altitude. That's the more, I guess, technical term for it. This is the altitude of this triangle, which is just the distance from the vertex up here to the opposite base. And this is indicating that this dashed line, makes a right angle here. This is going to be important for some of the work we do in this section as well, or in this unit. The fact that I have this altitude here, h, is taking my oblique triangle and essentially dividing it into two right triangles. this one right here, and this one right here. That's going to be useful for some of the work that we do coming up. But let's answer a couple of questions just using this fact that I mentioned right here. Again, this is called the triangle inequality, typically. If A is equal to 3 and B is equal to 10, can C equal 12? Well, these are two sides of a triangle, and we know that the sum of any two sides of a triangle, 3 plus 10 in this case, always have to be greater than the third side. Is this inequality true? Of course it is. 3 plus 10 is 13, and that's definitely greater than 12. So this does not violate this fact. The answer here would be yes. Another question. If A is equal to 10 and C is equal to 30, so here another two sides of that triangle, can B equal 35? Well, the sum of these two sides, I put the wrong thing here. I wanted this to be a 65. Let me change that. Can B be 65? In this case, if I add up these two sides of this triangle, 10 plus 30, that's equal to 40. And the sum of those two sides, 40, is still smaller than the third side. This violates the triangle inequality. This is impossible if these three values are to be sides of a triangle. So the answer here is no. Okay? Fairly simple. You just pick the two sides that you're given, add them, compare them to the third side, and then use that fact to make a determination. All right. This next question does not involve that fact that we just talked about, but it is something that's going to be pretty close to what we're doing in sections 10.1 and 10.2 in the parent class. So here we're giving some values to some of the things that are labeled up in that triangle. Alpha equals 43 degrees and H is equal to 10. We're asked to find C. Alpha and H are given to us. We're trying to find C. Now if I come up here, where do alpha and H appear? Here's alpha and here's H. C is this side right here. Okay, and remember what I said is that this H, this altitude of this oblique triangle, is taking my larger triangle and cutting it into two right triangles. Alpha, H, and C all correspond to measurements within this left right triangle over here. That's weird to say, left-right triangle. The right triangle appearing on the left. So let me just redraw only that right triangle. Okay, remember, this was alpha. Whoops, put that up a little bit. This was alpha down here. And we're being told that that's 43 degrees. H is the altitude, which was this guy, 10. C is the side that we're missing. This is now the type of problem that you would have encountered back in Chapter 7, solving for a missing side in a right triangle. What I do is I try to find a relationship between the angle and the known side and the side that's missing. I have an opposite side to my angle and a hypotenuse, indicating I should use a sine. Sine of 43 degrees equals opposite, which is 10, over hypotenuse, which is C. Isolating the C, I get C equals 10 divided by sine of 43 degrees. Okay? I realized I didn't work this one out ahead of time. Hold on, let me get my solution. 10 divided by sine of 43 degrees. This comes out to approximately 14.663. Throughout this section, we are going to be looking at rounded values for our solutions. 10.2 and 10.1 in the parent class, we're going to be doing the same thing. So normally, I've been saying throughout this class, we want exact answers. Leave things in terms of pi, leave things in radical form, stuff like that. But for the purpose of finding these missing sides and angles, this is one instance where we actually will plug things into a calculator and get a rounded decimal. All right, second fact that we want to talk about. I believe this is the one that's normally known as the Hinge Theorem. Let's suppose that you have two angles in a triangle, and for this purpose I'm going to call them angle A and angle B. And then let's suppose that they also have opposite sides, lowercase a and lowercase b. So lowercase a is opposite angle A, and lowercase b is opposite angle B. There is a relationship that's always true if we compare these angles and these sides. If angle A is greater than or equal to angle B, then that's going to imply that side A is greater than or equal to side B. Okay, so take a look at this picture again. Let's suppose we wanted to compare angle alpha and angle beta. And let's suppose that we knew angle beta was the larger of these two angles. It kind of appears that way in the picture, but you can never really trust the picture completely. But I'm going to say, let's suppose beta is a larger angle than alpha. Then that fact on the other page would imply that side B is also larger than side A because they are opposite the angles that compare in that way. So let's look at a problem where we need to use that fact. Let alpha equal 43 degrees and let beta equal 70 degrees. If A is equal to 20, can B equal 17? And how do we use this fact to determine yes or no on this question? Well, which of these two angles is the larger angle? Beta, it's 70 degrees. This fact up here would say that if beta is the larger angle, then B needs to be the larger side. But it's not. So that means this contradicts that fact, so that's false. And we need an explanation. So I would say no, because alpha is less than beta in this case, but A is greater than B. We shouldn't have this flipping of the sign happening here. Okay? That's a valid or a sufficient explanation. Okay, a couple more problems, and then we should be good for this section. So now we're kind of doing a little bit more of what we did in this example down here, finding a missing side. So let's suppose we're given this information. A is equal to 10, C is equal to 8, and H is equal to 5. I want to find B. Let's look at where that information appears. We're given A and C, but we're asked to find, A, C, and H, and we're asked to find B. Is that right? Yeah. So I'm given information that appears in both of those right triangles. I want to draw that entire picture over again. So let's take a look. Okay. C appeared over here in the original image, so that's equal to 8 in our example. A appeared here. We're told that it's equal to 10. And H is the altitude. We're told that that's equal to 5. Okay? B is that entire base of my oblique triangle. But what I'm going to do, again, wanting to think of these in terms of two different right triangles, I'm going to take B and split it up into two parts, X and Y. X is going to be the base of this right triangle. Y is going to be the base of this right triangle. If I can find X and Y separately, then I can just add them together to get B. And that's not hard to do because, again, that allows us to work with right triangles, which we're familiar with. Here is a case where I'd want to use the Pythagorean theorem. So for my Pythagorean theorem, x squared should equal my hypotenuse squared, which is 8 squared, minus my other leg squared, 5 squared. X squared in this case, that's 64 minus 25, which is 39. So x is equal to the square root of 39. Remember, in this section, we are working with approximate values. So the square root of 39 is approximately 6.245. I'm going to do the same thing with y. Y squared from my Pythagorean theorem is equal to 10 squared minus 5 squared. That's 100 minus 25. So y squared is equal to 75, which means y is equal to root 75. Plug that in a calculator, that's approximately 8.66. So this means b is approximately the sum of these rounded values for x and y. 6.245 plus 8.66, which is equal to 14.905. This is a common thing throughout mathematics, taking a potentially complicated problem and breaking it up into easier parts. I wanted to find the base of my oblique triangle B, and I had to break it into two parts, which were easier to find on their own just by using the Pythagorean theorem. And then I added those together to get my actual answer. One more problem, and then we should be able to wrap this up. we're given some more information. Gamma, remember that's an angle, equals 15 degrees, and h equals 24. Find A. So let me return to our original picture and see where gamma, h, and a all appear. Gamma, h, and a are all parts or measurements within this right triangle appearing on the right side. So I'm going to redraw this right triangle, but fill in the information that I know. Okay, it looked like this. We were given h, which was 24, and gamma, which was this angle right here, 15 degrees. We were asked to find A. This is very, very much the same type of problem that we did on the previous page. So it's going to follow the same pattern. I just want to set up a trigonometric ratio here that I can solve. Again, I have an opposite side and a hypotenuse, so we're using sine again. Sine of my 15-degree angle is equal to my opposite side, 24, over A. Now we solve for A. With a little bit of algebra, this becomes A equals 24 over sine of 15 degrees. And again, we're even though this has not been the norm up until this point, we are looking for decimal approximations here. This goes into a calculator, and I get 92.729. Done. Okay, that's going to wrap it up for this week.